Hi, so we'll be learning about two more page replacement policies which are most frequently used and least frequently used. So, in most frequently used, uh, the page that has been used for the most number of times will be replaced. Okay, so so it is a counting algorithm, and so let's start. We'll learn more about it during the process. So as you can see, the CPU requested page number one of a process. Okay, and this is your main memory, and main memory has a size of 3 frames only. Okay, so now here CPU requested first page, and the current frames are empty. So page one will occupy 1 frame. Now CPU requested second page. The second page will occupy another blank frame. Now CPU requested page. It will occupy this frame. Now CPU requested third uh, third page. Now let us also maintain a count. For example, page number 0, page number 1, page 2, page 3, and page 4. And this is the usage count. Okay, so here you can see currently page 1, 2, and 0 has been used. So their count is 1, 1, 1, and all others have been used 0 times. Now CPU requested page number 3. Now page number 3 will replace which existing pages? 0, 1, or 2. So as you can see, all 0, 1, 2 have equal frequency. They have been used for only once. Okay, so there is a tie. You can see whenever there is a tie in the selection, then it will be resolved by FIFO. So it depends from implementation to implementation, that whenever a tie happens, then which page replacement policy will be used. So here in this example, we will be considering FIFO as a tie. Now from 1, 0, and 2, who came first according to first in, first out? So 1 came first. So therefore 1 will be replaced. So 1, 2, 0, 1 will be replaced by 3. So now 3's count becomes also 1. Now 0 is again requested. As you can see, 0's count will be increased by 2. Okay, and here you can see 0 is already present, so 3, 2, 0. It is not a page fault, okay, because 0 already present in the main memory. Now CPU requested fourth page. So from 3 to 0, you can see who has the most count. From 0 to 3, 0 has 2, 2 has 1, 3 has 1. So 0 has the most count. So 0 will be replaced. Okay, so 3, 2, 0, 0 will be replaced by 4. And the count of 4 will be increased by 1, which becomes 1. Okay, so now it is 3, 2, 4. Now you can see 2 is again requested, but 2 is present, so it is not a page fault. And the frequency of 2 will be increased by 1 and becomes 2. Now CPU requested page number 3, and 3 is already present, so it is also not a page fault. So 3 and 3's frequency has been increased by 1 and becomes 2. Now the CPU requested page number 0. Now you can see from 3, 2, and 4. From 3, 2, and 4. So you can see from these, it has, so 2 and 3 has the most frequency. So there is a tie. And how will we resolve the tie? Using FIFO. So from 2 and 3, who came first? So you can see here, so 3 came at this point, okay, and 2 came at this point. So who came first between 2 and 3? 2. So 2 will be replaced by 0, and 0's frequency will be increased by 1 and becomes 3. Okay, now CPU requested 3, and what we have in the main memory? 3, 0, and 4. So it is also not a page fault. Now CPU requested 2. Now who will be replaced from 304? So 3 has 2, 4 has 1, and 0 has 3. So 0 wins. So 0 will be replaced by 2. So this is how you maintain a mapping between page number. So this is your page number, and this is your basically a count of how many times the page is referenced. So, so that's how the most frequently used policy is uh, used. Okay, and now you can see there is another policy called LFU. Okay, so this is also very similar. It is least frequently used. So here the page that has been accessed for fewest time will be replaced, and whenever there is a tie we will be using FIFO to address it. So here also you can see maintain a table 0, 1, 2, 3, 4. Okay, this is your page number and this is your count of how many times this page is accessed. So currently the count of all the pages is 0. Now CPU requested 1. Okay, so 1 will occupy this frame and the count will be increased by 1. Now 2, 2's count will be increased by 1. Now 0, 1, 2, 0, and 0's count will also be increased by 1. Now CPU requested 3. So you can see out of 0, 1, 2, who will be replaced for the fewest time. So all are used for ones. Okay, so there is a tie among all three pages. So who came first? 1 came first. So now 1 will be replaced by 3. Okay, now 3's frequency is also increased by 1. Now CPU requested 0, so 3 to 0, 0 is already present. That is not a page fault, and 0's frequency will be increased by 1 and becomes 2. Now CPU requested page number 4, so 3 to 0. Who has the least frequency from 3, 2 and 0? So 0, 2 and 3. So you can see 2 and 3 has the least frequency of 1. So from 3 and 2 who came first? 3 came at this point and 2 came at this point. So 2 came first. So 2 will be replaced by 4 and 4's frequency will be increased by 1, and here you can see 3, 4, 0. Now CPU requested 2, who all are present? 0, 3, 4. So 0 is used for 2 times, 3 is used for 1 and 4 is used for once. So there is a tie between 3 and 4. Who came first? 3 came first. So here 3 will be replaced by 2. Okay, now 2, 4, 0. So CPU requested 3, but the pages present in the main memory are 0, 2 and 4. Sorry, you have to increase the count of 2 by 1. So it will become 2. Now 0 has a count of 2, 2 has a count of 2 and 4 has a count of 1. So here the clearly the page number 4 has been accessed for the least time, that is once. So it will be replaced here. Okay, it will be replaced by 3 and the count of 3 will be increased by 1. Now Z2, 3, 0. CPU requested 0 and 0 is already present. It is not a page fault. 2, 3, 0. CPU requested 3 and 3 is already present. It is not a page fault. 2, 3, 0. CPU requested page number 2. 2 is already present. It is also not a page fault. So, so this way you can see that how most frequently used and least frequently used policies work. Thank you.